Hey guys, we're going to look at some sequences today. Arithmetic and geometric sequences, and sequences as function rules. There's all kinds of cool math sequences that we can examine. My favorite is, was, and always shall be the Fibonacci sequence, which is pretty sweet. It starts with 0 and then 1, and then each successive number is found by adding the two that came before it. 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Fibonacci was pretty cool. There's all kinds of really sweet ways that this sequence can be found in nature and the stock market. It's crazy how many cool things you can do with the Fibonacci sequence. So that's something cool to look up. We're going to be looking specifically at types of sequences and using sequences as function rules, or using sequences to write function rules. Okay, lots of definitions, all of them you need to know. A sequence is an ordered list of numbers. So it could be any list of numbers, but it's in order. So it starts with the first one and goes through either to the last one or until you have a rule that repeats indefinitely. Each term, each number is called a term. So each number in the sequence is called a term. When the difference between two consecutive terms is the same, that sequence is called an arithmetic sequence. And that difference is called the common difference. Anytime you do skip counting, you have an arithmetic sequence. 0, 5, 10, 15, 20, 25, ... Common difference of 5. And that is an arithmetic sequence. The vast majority of sequences that we are going to see in this video that we are going to use to write function rules will be arithmetic. In fact, all of them, will be arithmetic. When the ratio between two consecutive terms is the same, that sequence is called geometric. We could do something similar here. We can't start with a 0, though. We could start with a 1, and then times 5, times 5, times 5, times 5. I've run out of numbers that I know by heart in this sequence, and that's called a geometric sequence. They increase a great deal faster. Look. This one is 6 terms out and I'm only at 25. This one's only 5 terms out and I'm at 625. That ratio, when it's the same each time, is called a common ratio. Again, you will not see as much in the way of geometric sequences in this video. You'll see some in class, but we're going to now focus on taking sequences and using them. So let's look at some examples. Describe the sequence using words and then with symbols. Well, in this first one, you have 6, 7, 8, and 9. One way that we can take that sequence and organize it is to look at the number of the term, so the first term, second term, third term, fourth term, and how we can use that number to find the actual term. In this particular sequence, the difference of the term numbers is 1, and then the common difference of the actual terms is 1. So this is indeed an arithmetic sequence, and we said most of the ones we looked at for the rest of the video, actually I'm just going to rephrase that, all of the ones we're going to look at for the rest of our video are going to be arithmetic. The ones we're going to use are going to be arithmetic. Furthermore, in this particular sequence, we notice that the term itself is 5 more than the term number. So we can describe this sequence by saying the term is equal to the term number plus 5. So each term is 5 more than its term number. So there we have it. We've described the sequence in words, and we've described it with variables and symbols. Let's look at the next one. 4, 8, 12, 16. Now clearly you can already tell what's up. You can already tell that it's an arithmetic sequence because it's getting bigger by 4 each time. So that common difference this time is 4. So we recognize that. See if you can make the little table to match the table we made for the first sequence we had here. And there's our table this time. The difference of the term numbers, again, is 1. And most of the time, well, actually all of the time, because we're talking about a sequence with the first, second, third, fourth term, that's going to be what we have. The difference of the term numbers will be 1. The common difference this time is 4. It's 4. So this time, how do I relate term number t to, or excuse me, the term t to the term number n using the information I have? Well, I've got to look at it, and it's got to be a little bit of problem solving here. Here, each one was 5 larger There was no factor I could multiply by. Here we could say, is it 3 larger? Well, that would make this a 5, not an 8. So maybe it's not adding, maybe it's a multiplying rule, and indeed it is. It's 4 times. So 4n. T equals 4n. And that means that each term is 4 times the term number. So how can we use this in real-world style problems? Well, we absolutely can. There's a whole bunch of ways we can. Like in problems like this. Write an equation that describes the sequence 7, 10, 13, 16, and then find the 15th term. So that would require us writing it all the way out until the 15th term. Now that's tedious. That's not something I want to do. Instead, I'd like to find our equation to match this circumstance and then use the equation to find the 15th term. So what's happening this time? Term number and the term. So the first term is 7. The second term is 10. The third term is 13. And the fourth term is 16. So term number does increase by 1. The terms themselves increase by 3. So in each problem, in each of these, how am I supposed to take that information and figure out how to put that into a rule? Well, this time it's not 1 times 3, because as you notice, 1 times 3 would not give me 7. And it's not 1 plus 6, because 2 plus 6 would not give me 10. So what I probably have is both a multiplying and an adding rule. And you can use this 3 as your jumping off point. Always start by saying, all right, 3 times the term number. Because that ratio, that's the common difference of the terms, that is probably a multiplier. In these patterns, that's how that kind of turns out. So we're multiplying 3 times the term number, and then what are we doing after that? Because clearly that doesn't give us our answer. 1 times 3, not 7. What do we do to that to get 7? 1 times 3 is 3 plus 4 to get 7. So in this case, is this the correct rule for this situation? Well, let's try it with the other ordered pairs. 3 times 2 is 6 plus 4 is indeed 10. 3 times 3 is 9 plus 4 is 13. 3 times 4 is 12 plus 4, 16. So this rule does work. So to put it into words, multiply the term number by 3, then add 1. Now we have to take that information and find the 15th term. How do I find the 15th term? Well, you have a formula. N, remember, is your term number. It's your term number. So if I want the 15th term, I want to set n equal to 15 and use my little formula that I have. So t equals 3 times 15 plus 4. 3 times 15 is 45, plus 4 is 49. And there you have your 15th term. And if I was to sit down and just keep adding until I went all the way out to my 15th term, I would indeed get 49. And here's my proof to you that you do indeed get 49 if you write it out. I did it for you, took a quick picture. So that's 15 terms worth. And see, how much easier was it to write that out? Well, it all depends on what you're trying to do and what term you need. Had I needed the 400th term, writing it out would not have been an option. All right, so that gives you an idea of how this could be utilized. Now we have a real-world example of how we can use this sort of pattern. So we're going to find a term. So again, we have a sequence. The diagram shows the number of square tables needed to seat 4, 6, or 8 people at a restaurant. How many tables are needed to seat 16 people? So this one is a little bit different. Okay, let's look at term number. Excuse me. Sorry, didn't mean to move it around on you. Term number and term. Well, the first term is one table with, it's a 4 top, so that means there can be 4 seats at it. How many seats at the second one, the one with 2 tables? 1, 2, 3, 4, 5, 6. You can see that right here, 6. How many seats when there's 3 tables? 1, 2, 3, 4, 5, 6, 7, 8. And it looks like it is indeed increasing by a multiple of 2. Okay, so we are adding 2. So that common difference here is adding 2. And we know our term number. Our term number is adding 1. So it's going up by 1 for the term number, up by 2 for the actual terms. Again, we know that this is probably our multiplier. So we're going to have 2 times n, and then we're going to have to add or subtract something to get these numbers. So 2 times n would give me 2. Plus what would give me 4? Well, that would be 2. Let's test that out and see if it works for the other ordered pairs. 2 times 2 would be 4, plus 2 would be 6, so it works there. 2 times 3 would be 6, plus 2 would be 8, so it works there. So that's our definite rule. This is a little different from the other question, though, because we actually want to know how many tables to seat 16 people. So they're asking you to actually find n, because n, that term number, that was also the number of tables in the circumstance there, was n, and this was the number of people you could then seat at those tables if you look up at the actual example. So we're asked to find n if t equals 16. Well, if you look at what you have for this equation, guys, you can do that. Just replace the t with a 16 and solve this equation. Two-step equation. Subtract 2 from each side, giving me 14 equals 2n. Divide both sides by 2, giving me 7 equals n. They need 7 tables to seat all those people. Now at this point, I would like you to go through and practice with these. I think that it would be smart for us to do a few of them, but not all of them. So you might want to copy them down and try them all. Great questions for me to throw on a quiz here and there. Describe each sequence using words and symbols. We'll do 1 and 3. And we'll do number 5. And then we'll go ahead and do number 9. So let's start with number 1. The first term is a 2. And we can describe it by saying that the term increases by 1 each time. So the common difference is plus 1. The common difference of the term numbers is plus 1. And what's the relationship? Well, term number plus 1 equals the term. So each term is 1 more than the term number. How about problem number 2? 3, 6, 9, 12. Well, again, that common difference. This time it's plus 3. So we know that we're probably doing 3 times the term number, and then maybe plus something, and in this case it's not. It is definitely 3 times the term number. The first term is 1 times 3, 3. The second term is 2 times 3, 6. The third term is 3 times 3, 9. And the fourth term is 4 times 3, 12. So in this case, each term is 3 times the term number. Onward to number 5. For number 5, I need to go in and do what I did for the previous problem example 2. Well, first of all, I need to think about what's my situation here. Well, term number, I have 1, 2, 3, and 4 terms. And those terms are 10, 11, 12, and 13. My terms are increasing by 1. So their common difference is 1, and it's positive. And that means I'm not multiplying this time. So I am just adding. It's term number plus 9 equals the term, which means that finding the 10th term should be super easy. It's 10 plus 9, or 19. 19. All right. One more problem. Here's the last one. Suppose each side of a square has a length of 1 foot. Determine which figure will have a perimeter of 60 feet. Well, again, term number, term. Let's look. We got 1, 2, and 3 figures, so we have 3 term numbers. What are the perimeters of each figure? Well, the first one, 1 foot on each side, so 4 feet. The second one, be careful. You got 1, 2, 3, 4, 5, 6, 7, 8. Let's count it one more time. 1, 2, 3, 4, 5, 6, 7, 8. And then the last one. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12. I can already see that common difference of positive 4, and my terms are counting by 1. And if you look at what that means, we have 4 times n. Are we adding or subtracting? No, we are not. And we want to know, when will our perimeter be 60 feet? Well, this is term number, or figure number in the case of this particular problem, and this was perimeter. So again, I can take and I can plug in my perimeter to find my figure number or term number. Dividing both sides here by 4, I get 15. It's the 15th figure. Will be the one with a perimeter of 60 feet. And that concludes our sequences and writing equations for patterns video. I hope you enjoyed it. I'll see you guys in class.